Let us start this lecture with a thought process. All forms of emotions, whether happiness and sadness, secretes the chemical reactions, basically hormones, in the body. One has to learn how to keep them under control to have a blissful life, because you will have to basically take care of secretion of your hormone through your mind. So, let us recall what we learned in the last lecture. In the last lecture, basically we have discussed about first order reaction, second order reaction and third order reaction, right. Today what we will do, we will look at also different kinds of reactions, right, little bit. Then we will move into elementary reactions, right. So, let us first look at reaction in series, right. That means the reaction will be occurring in series wise, the way we do the relay race. Relay race, one fellow will take one button and then give to other will run, that way. So, that is in series. Let us say A molecule is reacting with B, getting into AB, right, and this AB is decomposed into C and D. If I say this is reaction 1 and this is reaction 2, let us say this is K1 and this is your basically rate coefficient or reaction rate coefficient, or people call it also rate constant, right. So, for that, for the first reaction, what would be the reaction rate? That is dCAB, if I look at by dt, that means how much of molecule AB is, concentration is changing with respect to time, is equal to K1 Ca and Cb, right. I can say this is basically 3. Keep in mind that this is equal to, what is that, dCA by dt, yes or no, that is equal to also minus dCB by dt, because it is getting consumed, right. And for second reaction, I can write down in similar way, dCAB by dt is equal to what, minus K2 CAB, right. And of course, that you can say also similar way, minus dCA by dt, dC by dt is equal to minus dC d by dt, and that is equation 4. What we will be considering now, what is the net, what you call production of CAB, that we need to find out, right. If I will find out the net rate of change of CAB would be dCAB by dt is equal to K1 Ca Cb minus K2 CAB, right. Now, of course, if I know this rate coefficient and concentration of all these things, I can find out very easily, right. And if you look at the CAB at time is equal to 0, what it would be? It will be 0, because there is nothing CAB, right. In the beginning, what are the molecules are there? A and B, some initial concentration will be there, right. And C and concentration of C and D also will be 0, isn't it? Yes or no? For example, if I will plot it with respect to time, this is concentration, right. And in the beginning, what will happen? there will be A and B, I can say this will be AB will be changing like this. This is concentration of Ca and Cb. Of course, at this point T is equal to 0, what will be Ca in and Cb in. Keep in mind that this concentration need not to be same. I have plotted here, but need not to be same, right? There might be two plots, you can say think of, but here I am just drawing just a simplicity. But my point is not that. Like what will be at if you look at C and CD, it will be 0 to start with. Maybe it will be increasing, right? This is corresponding to CC and CD. Are you getting? I am just drawing it because I am assuming this concentration both are same, C and D, need not to be, it will be different maybe, right. But my point is not that, my point is to say that what will happen to the CAB? CAB in the beginning it will be 0, at the end of the reactions it may be 0 or may be very small values, okay. In between what will happening? There might be peak values. Are you getting? There might be peak values. This is your CAB. So therefore, one has to really concern about how to handle this series reaction, because it may be occurring in nature. Like in nature means when you are talking about multi-step chemistry, right, you may need to look at that, right. So that is another way of also looking at the parallel reactions, right. So we will be looking at parallel reactions, right. Let us say that A molecule is reacting with B going to the AB, right. I can say this reaction 1 and with a reaction rate coefficient or the reaction rate constant is K1. AB parallelly will be decomposing into C and D, right. I can say this is reaction 2. Keep in mind that there in other example what we see in the series reactions, basically AB is decomposing into C and D, but here AB which is the initial reactants, that is going to some other product, right. That is the difference, parallel, it is parallelly going on. Like you might be knowing today people are doing parallel computing, right. So the reaction is going on parallelly. A question might be coming to your mind, when this reaction 1 will be predominant, the reaction 2 will be predominant. Is that question coming to your mind? There might be some situation where reaction A will be very vigorously occurring and B will be taking a back seat, right, or they will be in the same rate. It is not really possible, or maybe possible, I do not know, I mean maybe some range, right. So when it will be, you think about it, I will discuss that little later on, okay. For first reaction, I can write down CAB, change in concentration of AB with respect to time is equal to K1 Ca and Cb. But if I will be more interested to find out dCA by dt is equal to minus K1 Ca Cb, isn't it? Because this is getting consumed, therefore K1 Cb. Now I can say this is reaction 3, because I will be, and for second reaction I can find out basically dCA by dt for the second reaction will be equal to minus K2 Ca Cb, right. Let us say this is 4. So net reaction, net rate of change of or Ca, right, would be dCA by dt will be minus K1 plus K2 Ca Cb. Right. This simply just you add equation 3 and 4 you will get, right. So, that means if you look at the reaction rate of molecule A, right, will be basically dependent on the concentration A and concentration B, and it will be dependent on also K1 and K2. Keep in mind that K1 is a function of what? We have already seen temperature. K1 is a function of temperature. Similarly, K2 is a function of also temperature, right. And for example, like at certain temperature K1 may be very high, that means that is the which one? Predominant, right. And at certain temperature K2 may be predominant. So, as a result, if you look at that way, you will have to take care of this parallel reaction, which is important, because certain range, let us say 500 Kelvin, certain reaction will be very important, like reaction 1 is important, but in the let us say something maybe 1000 to the 2000 Kelvin, maybe reaction 2 is important, right, because that is giving a higher values depending on your activation energy, right, kind of thing. So, therefore, you need to learn how to handle these parallel reactions and then reaction in series or series reactions kind of things. And all these reaction what we have dealt with, we are only considering the forward reaction, right. We are not considering reverse reaction or the backward reaction. Let us see how we will handle that. So, reverse reaction, if you look at, I am just considering, like because of fact that the chemical reaction may proceed in both forward and reverse direction, right. Of course, keep in mind that I had also discussed showing some data that the activation energy, pre-exponential factors and temperature coefficients need not to be same. That means reaction rate will be different, it won't be same. Let us say A is reacting and going to the product B with what you call reaction rate coefficient Kf, and when B is coming back to the A, that is Kb, right. So, net reaction rate of consumption of A will be basically Kf and Ca, right. And what will be, if you look at, if I write down this equation, this will be basically dt is equal to Kf Ca minus Kb Cb, right. And what I am saying, Cb is nothing but Ca initial minus Ca, whatever being consumed, that is nothing but your Cb, right. That means this is with respect to time at any instant Ca, and this is initial, the difference will be basically nothing but Cb. Keep in mind that this is true only for this simple reaction what I have considered. This need not to be true for if it is a bimolecular reactions kind of thing, right. Now, so what we will do now, I will assume the equilibrium, right. Generally what is being done, you reverse reaction rate need not to be there, but you can find out by assuming it to be equilibrium, right. They do that. Then above, for simplicity reason, and then above equation becomes, right, Kb is equal to Kf Ca equilibrium, right, because when I am saying this is 0, right, this is 0, then I am saying this is equilibrium, right, and this is also in equilibrium, right, when this is 0 at equilibrium. So, naturally what will be Kb? Kb is equal to Kf Ca equilibrium divided by Ca initial, that means this is Ca is basically at time is equal to 0, Ca is Ca initial, right. So, Ca initial minus Ca equilibrium, that means you can get this reverse reaction rate coefficient in terms of forward reaction rate coefficient, and of course, you know the initial values of concentration, you know the equilibrium values of molecule A, then only you can find out very easily. And this is the standard procedure what is being used because of simplicity reason, right. And then I can write down basically, if I say this is equation 1 and equation 1 becomes like dCA by dt nothing but Kf Ca initial, right, and Ca minus Ca equilibrium divided by Ca in minus Ca equilibrium, right. That means if you look at, right, I mean I can avoid this Cv, right, because I have already in place of Cv I put it here in this, and then I am getting this relationship. So, if I will integrate this by integrating above equation, like I can say 2, I can get this dCA minus C equilibrium divided by Ca in minus Ca equilibrium, Kf Ca in divided by Ca in. See, always there will be some constant and you will have to evaluate, you know, C at the initial t is equal to 0, that will go away and then you will get final result, right. So, this will be basically final result what you will get. You can do that and then find, if you will find difficulties, we will see how you can. So, by that what will happen, I can also by knowing this Kf, right, I can handle, right, because I can find out what is the how the Ca is varying with, right. Keep in mind that here we are taking the at equilibrium dCA by dt is 0, that means, you know, that is the equilibrium condition we are considering for the calculating the backward reactions, right. So, if I look at this way, like I can, if I know the Ca, right, if I know the concentration of Ca, I can also find out what is the Kf, because all are known, this equilibrium will be known, this will be known, right, and if I measure the Ca at certain time, right, then I can find out what is the Kf, right, even if I do not know the Kf for this simple thing. So, let us take an example, like, you know, how to determine the backward reaction rate coefficient, right. So, this example is reaction rate coefficient for chemical reaction NO plus O going to the N plus O2, right, and the reaction rate coefficient is given by this Kf, like it is, if you look at this is your pre-exponential factor, this portion, right, right, and this is of course your this is temperature coefficient, in this case B in our this thing is equal to 1, right, T, and this is your exponential factor, right. And keep in mind this is centimeter cube per gram mole second, and we will have to determine the backward reaction rate coefficient Kb at 2300 Kelvin, right, 2300 Kelvin. So, what we will have to do for this? What we will have to do? Because we know the chemical reaction is given, right. This is a very famous reaction, right, N plus O2, right, and this can take place in the both the direction, right. I can say Kf, and in the backward direction this is Kb. So, I can write down the concentration of the NO, or the reaction rate of NO by dt is equal to minus Kf CNO CO plus Kb Cn CO2, isn't it, right? And for that what we will do, we will basically look at equilibrium what is happening. Like at equilibrium, NO dt is 0, right. If that is 0, if I say this is equation, then equation 1 becomes, right, Kf by Kb is nothing but Cn CO2 by CNO CO. And keep in mind that this is nothing but your what? Kc, right? Can I say this is equal to Kp? Equilibrium constant, this is big capital I am writing, okay. Because bimolecular reaction, so therefore the pressure by this term RUT it won't be coming, okay. So therefore it is possible only one, and keep in mind that Kp is a non-dimensional parameter, right. And what is that Kp? Kp we know is nothing but exponential delta G T naught divided by RUT, right. Now I will have to evaluate this one, right, delta G naught. For that data is to be given, and taking data GFI values, right, from thermodynamical table, right. I have already shown you table, it is there on the back side of textbook also. So you can find out delta G T naught is equal to GFN naught plus GFO2 naught, right, minus GNO F naught minus GFO naught. Now of course, is it true, because all are these things, so that is fine. So this O2, if you look at, O2 will be 0, right. If I will substitute these values, right, these data of GFN and GFNO and GFO I will be taking from the thermodynamic table corresponding to what temperature? 2300 Kelvin, right, at, right. So I will just put these values here, because I am not getting to table, but you will have to do or given table, go to table and solve. 631 plus 0 minus 61243 plus 101627 is equal to 163,461 kilojoule per kilomole. Keep in mind these are evaluated, these values are evaluated, right, at 2100 Kelvin, right. Now if you look at these Kp values, I can evaluate very easily, and then from this expression, if I say this is equation 2, I am interested to find out Kb. So Kb will be nothing but your Kf into Kp, yes or no, right, and Kf is given to you, right. So and Kp you can evaluate because you know this thing. So, let me write down here, that is E delta Gt RUT minus, right, RU you know T is not, but I will have to find out basically Kf. Kf I know is very easily I can find out from this expression is given 3.8 10 power to 9 into 2300 for this temperature into exponential of 208202300, and this happens to be Kf. I am getting 1.024 10 power to 9 centimeter cube gram mole second. So, if I will put these values here, right, 1.024 into 10 power to 9, right, E, this is 163461 divided by 8.314 into 2300. If I will substitute this value, you will get, right, something 5.28 into 10 power to 12 centimeter cube, right, gram mole second. So, this is my Kb values, right, 5.28 10 power to 12 centimeter cube gram mole second. So, if you look at your Kf is 10 power to 9, whereas Kb is 10 power to 12, you know, like of course, there is a 5 also coming into picture. So, it is a reverse reaction is what you call having higher reaction rate coefficient, right. So, by this way you can really evaluate the reverse reaction. Keep in mind that we are taking that equilibrium as a condition, like it is attaining equilibrium then only. So, with this we will stop over and we will discuss about what you call elementary reactions further in the next lecture. Thank you very much.